rewards are also provided, 0, 0, 0, 0, 0, plus 1, plus 6. There is an evaluator. I'm going to evaluate the rewards on the cell, and if the reward is higher than 0, I'm gonna go for it. Yeah, I want to maximize my utility. There is a transition function that maps every state with a specific input. A state is where I'm gonna be in the different squares, okay, and the input that I'm gonna get if I move to those squares. So if S is the current state for all actions that exist in the environment, in the possible action that I have, I'm gonna set a reward for that specific action. If I go up, I'm gonna have a specific reward. If I go down, I'm gonna have another reward, left, another reward, and right. So what do you do? How do you solve this problem? Well, the first idea might be just expand in all directions. I just gonna expand in all directions, and I'm gonna look into the four different possibilities. This algorithm is relatively easy because, as I told you, it's brute force. I'm just gonna be looking into everything that it is closer to me. Yes, I'm gonna look into all these four different possibilities. I'm gonna find out what is the best one. I'm gonna evaluate the four different possibilities. I'm gonna choose which one is the best. So I'm start searching from the root node of the tree, which will be 2.2. And then I will expand to the next node, which will be 1.2, 2.3, 3.2, and 2.3. Yeah? Now, there is two possibilities now. I take the +1 or I take the +6. Why I'm taking the +6? Because I want to maximize my utility. Let's look into this problem. What do we do now? I know the problem that I have with the breadth first search is that I'm going to be looking to the problem now, and I cannot assess. I want to evaluate my actions 1.3, 2.2, and 1.1, and I get 0 from all of them. So what will be my next step? If I continue working with the same algorithm, I'm going to expand myself to 2.3 and 2.3 and 3.2. I'm sorry, it's an error. 1.3 and 2.3. 1, 2. So it is myopic in the sense that it cannot see the future. It will not plan about the future. It was going to be just planning about today all the time. What will happen if I have in the position 1.3, I have a +10? I'm going to evaluate that situation. I'm going to say that my utility is higher than 0. I'm going to take it. So I'm going to end up in a optimum, but it is not the global optimum. It's one solution, but it is not the best solution to the problem. Right? Do you follow? Well, this is what we are seeing here. It works for problems in which you only have one optimal solution, or the optimal solution is easier to reach than problems in which you might have multiple solutions that might not be optimal. So how does it work? I have been talking before about the search tree. Well, the search tree can be represented by something like this. I'm starting in level S, and I'm going to look into first option A. I'm going to evaluate it. I'm going to move to B. I'm going to evaluate it. If these two options are not providing me with utility, then I'm going to look into all the rest of possible options, C, D, G, H, and so on. So in each step, I'm going to look into something else. If I reach a utility that it is higher than 0 and it already provided me, it is already good enough, like for example here, I'm going to stop because I already got something and that's going to be enough. It's 0, so 1 is better than 0. Therefore, it might find less optimal solutions for some instance, okay, or of other problems. Other problems that you might have. The first problem is the time complexity. You have to go through all the nodes in order to choose what is going to be the best path or what's going to be the best solution. So it increases over time. You can see here how does it increase. And also you have the problem of the space complexity, which is given by the memory size. So you have to know everything that you have seen until now in order to be able to afterwards decide what is the best path. Do you want to have a look at this? How does it work? Well, we have, see if I can move it. No. We have the starting point, it's going to be the green point, and the end point, the goal, is going to be in the red. I'm going to choose my breadth first algorithm. I'm going to start searching for a solution. I don't know if this is going to be working. Oops, give me a second. Let's reset. Wow, come on. So as you can see, the optimal length is going to be 10 squares. The time is going to be 5.87, and the operations are 843 in order to reach the goal. What's going to be for me to find where my keys are. So the more I'm looking into specific places that are away from me, then I might be able to find the solution. What is the good thing about this algorithm? That if you continue expanding and expanding, at some point you're going to find the solution, isn't it? It just takes time. How can we improve the algorithm? Or what can we add to the algorithm? I already told you about it. It's like we can add some kind of costs that are related to what? To the movements, to the states. So if I have a given state, I can use the GN, which will be the cost associated to moving from one place to the other. And this is what we call the uniform cost. So I'm going to be now not focusing on how far I am and moving one square after the other, but what I'm going to do now, it's going to be looking into how much does it cost me to move from one place to the other. You might be asking yourself, okay, but if the costs are the same, probably you are looking into the same thing, and that's right. But if the costs are different, maybe you will find different paths. And this is like just a question from I think stock exchange, but I don't remember if it is AI or computer science. So when do you think that you want to use the uniform cost search? What kind of problems do you think that you can solve with this? No idea? Transportation is a topic, yeah, where the algorithm is being used, yes. So you have to find out how to go from point A to point B, but you are going to take into account not only the distance, but the cost associated to going from that place to another. So, and then maybe you have different kind of networks. What else? Have you used Omio? Do you know Omio? What is it? Yeah, but how does it work? What is the idea behind it? Okay, and then you can decide how to go from Munich to Madrid, for example, and it will be focusing on the cheapest or the fastest. And what will be then the cost associated? In one hand it will be time, and the other one will be euros, right? So such an easy algorithm, and they built a website on it, and they are selling stuff. What else can we use? For what else can we use this kind of algorithms? Let's say that I am planning a new neighborhood. I have to build. I'm going to build 200 houses, and I have to decide how to connect all of them through an electric grid. Can I use this algorithm? Maybe yes, I can connect all the nodes together and then try to find out what is the shortest distance between them based on cost function, which might be the cost associated to installing different kind of cables. If it is aerial, if it is going to be underground. So this algorithm, it is relatively famous, and it's been used currently. So how can we find a solution for these myopic algorithms that are not taking into account the future, let's say, or steps ahead of the current state? We can use heuristics, and heuristics are rough estimates on how far it is at least to the target. So how much do we need to move in order to reach the target? Now, the important thing is that, again, and you don't have to forget it, is that you still have a fully observable environment. You still can see where everything is happening. The heuristic function, h, we can call it h, estimates the value indicating the utility of states, of the different states that we are going to take. As we have seen before, it can be done by h. We didn't use it before, but it was expressed, and estimates how close a state is to the goal. Designed for what? For particular research problem, and you can use different kind of distances. For example, the Manhattan distance. You already know what the Manhattan distance is? The Manhattan distance and the Euclidean distance. We are going to see these distances afterwards also in clustering. They are being used all the time. These heuristics are being used all the time in algorithms. So let's see that we have this kind of grid. And we are here. The Manhattan distance, it is called Manhattan because Manhattan has been planned also in a grid system. So if you want to go from the 7th Street to the 5th, you will have to go always like this. And if you want to go to the 7 with the third, you will have to go maybe like this. You are not allowed to go crossing buildings. Yeah. If you are allowed to close to go from one, and you can draw the shortest path between these 2 points, let's say, then what you have is the Euclidean distance. You know the Pythagoras theorem. Okay, so you have A, and you have B, and then you have to solve this. That is the size of this diagonal. That's the Euclidean distance, and that's the Manhattan distance. Right? So in a Runkus world, when the archer is here, the archer is not allowed to go here. This requires 2 actions. First, you have to go here, and then you have to go here. Right? The archer starts looking into this direction, into the right direction. This is why, if you want to go to this place, as the utility function for one move is -1, the archer will have to first move, so rotate 1, and then go here, and then go here. It's going to be post associated that are -3 compared to -2. So based on the utility function, for the archer, it is always better, in the example that we have seen, to go first to that square. Now, what is this heuristic function? How do we define the heuristic function? So let's say that we have, and we know that we have our archer, and we know that it is 100 here. We want to reach there. Well, we can define a heuristic for each one of the movements that we can take as for the actions and the different states, right? So if I can move only 1, I cannot move in diagonal. I know that for reaching this point here, it will take me 91. It's 1 step. If I'm here, it will take me 2. Here, it will take me 2. Right? If I'm here, and we continue to populate. I'm not sure if I'm doing this right, just thinking fast. Like this? Maybe. I think so. So you see, now what will be the heuristic here? Choose the path. Okay, in this case will be this one that allows you to reach the goal by minimizing the utility or the distance that you have to your goal. Here is the example. Remember, fully observable, agent has always access to the complete state of the environment and observational state of the environment. So with heuristic, it is very easy to implement logic reasoning for agents and enables them to prefer expanding states that are estimated to be closer to the final goal. And the concept of preference is very powerful, as it can be used. It is being used for many algorithms that you might know. Like, for example, let's think. algorithms that you might know. Algorithms that you know about machine learning. Gradient descent, have you ever heard of it? Gradient descent? Never? Okay. Well, it is based on the same ideas. Here our robot, again, is following. So if you have also a cost associated to different action, yes, now you have two dimensions that you can take into account. So now what you know is that there is going to be a kind of heuristic associated to my next move, but also a cost associated to that specific action. So then based on the sum of those two costs, the cost of getting far away or getting closer, plus the cost of moving from one place to the other, I can decide. In the case of the archer, the problem that the archer has is that moving, rotating, it costs -1, right? So it's going to be trying to move and rotate as less as possible. So what then will be like the optimal path? And do you do the same when you walk through the streets? Probably not. But if you're in Manhattan, never either. So you always try to like yeah, makes sense. Because you don't have cost associated to turning to the left or to the right. At least that you have to wait for a ample street light, and then you decide, oh, there is a street light there. Let's go this street because there is a zebra pass at the end, and then I will cross, and then I will go in that direction. And this is probably a heuristic that you are using. You don't know how you are using it, but your brain is using it. And this is how this is also connected with psychology. So we humans, we have learned about these heuristics over time based on experience. Computers, they cannot. So we have to provide them with information or algorithms they don't know. We have to provide them with a set of rules, you know, to follow behaviors that are similar to the behaviors that a human might take. And this is artificial intelligence. Because they look somehow intelligent. There's some kind of reasoning that is logical behind it, that you can infer and you can say, okay, I think that this is an optimal solution for the problem that a human may come up with. Okay, let's see if we can have another example. I think that I have the same problem. You have the link also in Island. If you want to play a little bit with it, you can see the different algorithms and follow. So let's try the Dijkstra algorithm. It's not allowing me. No. Oh, I hate this. Give me 1 second. There's an improvement. Let's look into best first search. And now with different distances metrics. You see, it's much Much better. So what you can also do is you can add walls. And now let's look on how do they behave. So much faster. Yeah, it is on the Island course. You can go to the Island course and you will find the link to the website. And it actually is a GitHub. So you have that. Sorry? Let me check. Yeah, I think that it is you have it's a GitHub page, but it might be both. It's a github.io, but probably you can find the code associated to it. Finding this one. It is, as I said, the link is there. So go to the website and try to play a little bit with the three algorithms, creating walls and eliminating them to see how do they behave under different conditions. Let's see if you can find out rationally why some algorithms are better to others in a specific context. Because each algorithm, it is better for a different problem. It is not that there is an algorithm that is the best always for a specific, so for all the problems, but the specific algorithms might be solving a specific problem better than others. So try to find out, like if you have something like this. No, no, okay, not working anymore. So what is the IDA algorithm doing? Can you try to understand what is going on? I think it's going on with the ADI. What is this? What might be this algorithm about? Sorry? Yes. And one is going straight forward and finds the closest point, but then it doesn't understand where to go then. Yes, so somehow it's something like let's think in a tree. I have a set of different options. I think the Manhattan distance is, yeah. I have 4 different places where I can go, right? I'm gonna try always the closest one. So the one that minimize the distance to the final goal, because I already know where the goal is. And I have 4 more, and then I might have 4 more. The EDA algorithm, what it's doing is trying to follow this. And if at some point I might find that this is not the correct place to go, I'm gonna have the opportunity to go back and restart. The problem that you have is that if you are not, this is a metric. If this metric is not high enough, you might have the problem that going back to the same point all the time, so here, and getting into a loop, because you cannot get out. So you can, what I want to say with this is that even if you are thinking on algorithms that might be more complex, and in specific frameworks or contexts, they might be behaving very well. In others, you want to go for this more based on brute force, or that might be that have less risk of entering into a loop, so that they can always provide you with an optimal solution, or at least a solution, even if it is not optimal. Right? So, what is the Chebyshev distance? What do you think it might be? We have seen 2 distances. We have seen the Manhattan distance and the Euclidean distance. But what can be the Chebyshev? Have you ever heard about it? The last distance that we have here. I don't know how to pronounce Chebyshev. I don't know what is. Sorry. No, I know it's let's start now. Google it. Ask GPT. Whatever. And try to explain it to me in your own words without reading. Ehebishe. How does it look like? Just which one? Wait, don't let me alone. Someone? Can I repeat the question? Yes. Can you please define in plain words what the Chebyshev distance is? Yeah, it is related to distance, and it is related to two objects. So it might be this object.
So it's the direction, understand, further away from the target.
But it is the same for the Euclidean distance and the Manhattan distance. So this is right. So this is something commonly. So it's a distance. A circle. But a circle would be a radius, and that would be a Euclidean distance. Someone else can explain it in plain words? Yes?
Well, if you compare the two, x1, y1, x2, y2. We'll do like x2 x1 and y2 and y1. The absolute value of x2. And the absolute value of y2 is y1.
Oh, so big one.
Put like a max function, like a max meaning for two. And the other one is
And how do you explain this to a normal person?
that's really, but this is the ladder. This the ladder of the ladder value the one of going first, then left, we go left first. Right.
Okay. Exactly. We have one, two, I don't know, I think it's A, B, C, D, isn't it? We start with A. Someone like in the chest here?
One, two.
The letters are at the bottom. One is H is there. And we have one here or one at the top? One here, one is at the bottom. Let's say that we have the key here. At least, how much does the key needs to move in order to go up? One. And if he wants to move in the other, it's also one. That's the king. The queen is much better. Now, if we want to, we can continue. Right? So we can have two. That's right. Then three, and then four. The king doesn't want to move left. Why? Because it can go in all directions. And this is the idea of the Manhattan distance, okay? It's the king. the king can move the dial, and then is that if in Manhattan, the distance in this D1, and this was distance 1, and this one was distance 2, Manhattan. Now it's different. Now, in the Chebyshev, that's going to be a D1. What is the octane? What is the octane? Oh, sorry, the octane, the octile distance there. But yeah, you take what?
No, the open.
Yeah.
The diagonal.
Cambiar diagonal? Yeah, it can be, but it has some kind of penalty. Actually, for B2, we are going to take the root. So it's going to be 1.41 something, or I don't remember what is the root of 2, but something like this. So we are going to somehow do something like in between. Okay? It is not going to be 2 moves. It is not going to be 1 move. It's going to be something between 2 moves and 1 move. Yeah? The Euclidean? Don't know what is it? I mean, the Euclidean is if we have 1 point here, we are here. Or if you want, we are here. This distance is this distance, yeah, is shorter than this one. Right? So the Manhattan distance is going to be going here first and then here. The Euclidean distance is going to take the straight line between the 2 points. That's going to be the Euclidean distance. So depending on how do you define the space and the cost associated to the space and the distances associated to those things, you might have different algorithms that might make sense or not. Questions? No questions? So in the uniform cost search, as I told you, like you are looking into only on the cost that you might have. Okay, we only take into account this cost, so we are always going to be looking to paths that are cheap. Yes. If you need to know chess, no. It's just as an example that usually many people know chess about this. I mean, it's an example to explain it, but you don't need to know chess to write algorithms. What I'm trying to use is an heuristic. So a way of explaining you something based on past knowledge that you might have. From the psychological point of view of what is an heuristic. Right? Questions? What are the two difference? Okay, I'm gonna ask you, like, for example, you. Okay, so what are the two different definitions of heuristics that we have put today? One is and maybe looking around for this. Don't give me an example. Give me a try to define it. The difference between what is one thing and what is the other in your own world. Start from the beginning. Okay, who can improve this definition? Yes.
The one definition was that we have a search that we know our goal in it, or we know that the goal of that search.
The other one? Yeah, okay. And what would be the other one? Okay. Yes.
There's the informed and the uninformed. The informed is the one way you do the rule, and you outside and the people around you. The uninformed is where you have to that kind of.
Okay. I want to work on the okay. And try to find out what are the concepts of heuristic based on computer science and distances and search algorithms and the heuristic work meaning related to cognitive science. Important. 5 minutes. So for also for the people that are online, try to find out and write down what is the difference between the concept of heuristics in terms of computer science and heuristics from cognitive science. Please define. I'm going to write it down in a slide so that you can follow. For those that are online, I'm gonna create a breakout session. I'm gonna make, how many are you? 21. I'm gonna make 10. So you can do the exercise.
Okay, let's do it, ready?
Or 50 if you want. 15. 50.
But computers believe that with someone who collects the data. So depending on the data, they work, and depending also on the approach you want. you can make the algorithm do at least the rule.
So an heuristic is a way to provide information, additional information to the algorithm in order to choose a specific action. In this case, in search problems, we have an heuristic that will help the algorithm to make a decision based on what? For example, on the distance that we have. So we provide additional information. So we know what the goal is, and we know where the starting point is. So we can provide information about how far away are we from the goal. That could be an heuristic that it's useful. In cognitive science, we use them heuristics in a very similar way. Humans have some kind of rules of thumb, like general way of thinking, that it is based on past experience, on culture, on beliefs, and we use all of them to make decisions fast, without thinking. So we use heuristics in order to help us reduce the search space or to find a solution that maybe if it is not optimal, it's a solution that might work. So they are very related. As I said, we are going to be using the heuristics. In this case, the heuristic functions might be the Manhattan distance, the Euclidean distance. These are our heuristics here. We use the distance, the concept of distance, to help the algorithm understand how far are you from the goal. So if you are getting far away from it, maybe you have to reconsider in which direction are you expanding the horizon, the frontier, right? And we want to go always to spaces, to states where we are closer to the goal. Do you know Hansel and Gretel? What is it about? It's two kids lost in the forest with a piece of bread. And what do? And this is an heuristic. And this is what we are doing with the algorithms. We are telling the algorithm, you are on the right way. Do you know that this is what ants do? And this is the meta heuristic of ants. So let's say that you have an ant colony here. And there's some food. And they want to reach the food and get it before other insects or we find out that there are some that they are getting all the food for them. Ants are a little bit stupid. Have you seen them like behaving alone? They are nothing, but in groups they are very powerful. Why? Because an ant might be following a specific path, and other ants will be following another path. And every time that an ant is making a decision of which path to follow, in these points, the ants are going to leave some pheromone. Some pheromone that is, it's going to be identified by other ants, and those ants, they are going to be happy about this pheromone. They're going to be feeling, I don't know, like pheromone is, I think it is also called like the hormone for love. In this case, they are using it in order to identify right decisions. So if you have 5 ants, each one of them following the different paths and providing a pheromone every time that they choose the right way, going back and going forwards and back, what will happen over time? Yes, because the time that you need to go on this line, it is shorter than the time that you need to follow these other paths. So this ant following always, or the ants following always this direct path are gonna let more pheromones. So when the next ant is gonna be choosing which path to follow, it's gonna feel that this path is full of pheromones. So more ants are gonna be following this path. Do you understand the logic? This is what we call a meta-heuristic. It's a heuristic based on nature. And there are many others. Bees also behave like this, okay? Large groups of insects, they follow also heuristics, okay? And artificial intelligence is also based on, there is a branch of artificial intelligence that it is just based on these heuristics. You probably want to see these heuristics in the future, okay? This is why I need you to understand what an heuristic means and how to use them. In our search space, in our search problem, the heuristic is very simple. It's just providing information based on a distance, a heuristic distance. Yeah, heuristic is going to be the distance that provides information to the algorithm. How far are you from the goal? It means that we know where the goal is. So we have full information about the environment. So we can say, okay, you are too far away. Let's hot, cold. Have you ever played this game when you are a child? These are heuristics. So for you as a computer scientist, what is important, it is not just to code these things, but to understand what are you coding and what are you using, one heuristic or the other heuristic. Questions? Do you understand the concept of meta-heuristic with the ant colony? Does it make sense for you? Does it fit what was your thinking about heuristics on computer science? Probably yes, and it also should be able to fit also the concept of heuristics in cognitive science. Okay, then let's move forward. Yes? Because we are reinforcing the learning. Every time that we get a positive outcome, we reinforce the algorithms or the algorithm of the colony saying, yes, you're doing it right. So yeah, it's a reinforcement in the sense that every time that you get the label or every time that you predict. Yeah, look, this is what we are going to look into. Like, let's say that you have a problem. And you have to find the maximum of this function, yes? You might have a problem, and it's that if you start looking from here, what is the maximum? You might get stuck here, in the local maximum. When you actually know that the maximum is here, you will have to find an algorithm that allows you to do this. You have a 3D representation, okay, of the same space. There are algorithms, okay, that based on gradient descent, for example, or hill climbing, it will allow you to identify what is the overall. Maybe it is here also, or it is here, what is the overall maximum. So you have an environment and a space in which you have to explore what is the maximum, and there will be some algorithms that will be performed better or worse. There is in optimization problems, the best algorithm is Gurobi, is private. We don't know how it really works completely. It is a company. It's called it's a solver. Okay, it solves mathematical optimization problems, and yeah, the name of the company is Gurobi. You have to. It's the license is for free, but you have seen this probably many times in MATLAB and other mathematical software. So those algorithms, they can be also used to find solutions of optimization problems. Do you understand? Right? So the link, so these things can be used. It's like the logic course that we have at the beginning. logic can be implemented in machine learning in the way that we, for example, develop decision trees. But you can combine decision trees, multiple, and then you can do some boosting and some bagging, and then you will have random forest, and it's more complex. And then based on that, based on logic, you can also build neural networks, which it's using the logic together with probability. So we built upon all these concepts, okay? And there are some algorithms that are just using a specific set of tools or, tools, let's say, and others that are combining them. Do you understand? It's like a Lego. Other questions? Yeah, well, here in the best first search, sometimes it's also called the A. It depends on how it is defined, okay? Well, what you are taking into account is both the distance, let's say, or the heuristic, which is going to be the distance plus the cost of the action, okay? You can see here the different nodes and the different nodes have a specific heuristic, but moving from one node to the other might have a specific cost. Have you ever played, I don't know, like, have you ever played a computer game like Age of Empires or something like this? I don't know, I'm too old. What? Clash of... okay, good. But it might happen that you want to cross a river or something like this, and by crossing the river you need more time, isn't it? Here. That's exactly the same idea. Okay? So this is how it works. So by providing weights to specific spaces, we can also interpret them as, okay, it's going to be more difficult to go through this, or it's going to, so we can provide additional dimensions to the problem. This is again, so I want to jump into this. Greedy search with heuristic. Well, here we have like the same example, like you can go directly from S to G, but it will cost you 10. Now we will prefer to go first to A and then to C and then to G, because it's going to be costing me 1, 1, and 4 is going to be 6 compared to the others, okay? To the other options. There is also a nice website from, I think it's Stanford. I can provide also you with the link. Let's see if I am able. So the interesting thing about this website is that it is search theory applied to games. Well, you can see here. You can see you can understand this graph, okay? Like I don't know, like a Lord of the Rings thing, and you can see, okay, how can I get out from here? And then you have like the different steps. An algorithm based on problems related to weights for the different. So you have the breadth first search, you have already seen it, the JITKA algorithm, and the AI, which is the modification of the JITKA, that it's taking both the cost of the action and the distance. The JITKA, as we have seen, is just taking the cost of the action, and the breadth is the space that it's interested in. So you can see also here how it works. It's the same as we have seen before. And you can see how does it go from the different spaces. As we have seen before, you first look into A, then you look into B, then you look into C, D, E, and so on. In this case, it's with numbers, but and if you are interested, I mean, they have the code. Code is very easy. I haven't went through the code. I think that the only important thing for you is the frontier and the QA. So the waiting list of spaces that you want to explore, and then the number of spaces that you have already explored. So it's just a loop through the frontier that you have, and then you go from one to the other. These are the heuristics, in the sense that how do I find where I was coming from? So once you have explored the whole thing, yeah, what you can identify is if I have been exploring the space from A to 100 in this direction, I can also provide a kind of information on how do I reach the different squares? How do I expand myself to reach those squares? Yeah, and then you will be creating a vector, and this is the vector that it is following. So if I move the star, so the agent, I will understand how the agent is moving through the space. Same with the end. Yes, so that I can create the path and recreate the path that it is generated. If I modify these arrows, and instead of the arrows, what I have is an heuristic metric, or heuristic, which can be the distance, then I will find it. Well, I will upload the website to the island course, so you can have a look at it. It is very well explained, and it contains a lot of examples. I have seen that some of you are already playing computer games, so maybe you want to play with these computer games. Do you have questions about this? Do you understand now the heuristics? Now you understand the search problems. Now let's have a look to another important thing, which is the utility function. We already know how the actuators work. We already know more or less how the sensors work. We know that we can provide some kind of features that will be the heuristics. We now can define which kind of environment we need, what are the utility environments that we might have. We know that the set of actions is going to be provided and so on. Let's talk about utility. Utility is a function that is going to be assigning some kind of value for specific states. You have examples of value of pieces, captured or lost in chess. You might also have in robotics the distance to a goal. If we are thinking now, for example, in a robot that is taking some stuff from one production line to the other. The problem that we have with utility functions is that they are very problem specific, and how to define them depend strongly on what do we know about the agent. You have to look very careful in which the kind of utility functions that you are using, and I'm gonna show you somehow why. So AI systems can be think also on optimization problem. Yeah, what we try to do is to optimize what would be like the best outcome. So we have a set of constraints, and we have to find out what will be like the best outcome for us or for the agent. So we have to look into the solutions and pick up that one that is the best one, like we have seen on this example. Yeah, we know how to search for solutions, and we know that we can employ some search algorithms in order to find solutions. What we want to do is to find those solutions in this region that is feasible, that we consider that makes sense. I think 1 week ago, I provided you with an example, and I wasn't sure if maybe I can recap now from last year or from the other day. I don't know if you remember this. I asked you, like, if we have a regression model like this, Yes, we might find something like this. Do you understand that this is possible? What will be the value for B, for beta? For beta 1, 2. Well, it has to be negative, isn't it? It has to be negative. Because if not, it will be like this, going up, right? So it has to be negative. Which kind of problem or which kind of situation example can we think on things that over time they grow, but they grow the higher value of it. So we have function that grows through time, but the increases the value are getting lower over time. So for example, radiation, okay? Can you explain a little bit more?
The half-life is the inverse of the radiation gap and the radiation. And half was completely function.
Okay.
Horizontal amplitude. That's like the inverse of
The inverse of this one. Yeah, but I don't want the inverse of this one. So I want this one. And you can think of like, let's think in very easy examples, like huh? I want to have examples, yes.
There is a rule called the infinity. You have 20% of effort to get 80% of the results. And the 80%, the other 80% of the effort, 80% to reach 80%, 100% to do that.
Okay, wait, yeah, I understand that. Let's make something much easier. Humans, height, how tall you are, over years, okay? You grow, and then you get older and older, and then maybe you go a little bit smaller, right? But you know that it is not going to do like this, because it doesn't make sense, people that are 1 centimeter or, isn't it? When they are 100 years old, right? Do you understand the idea? So something that grows through time, but give me another example. Time study. There might be an optimal number of hours that you will be learning, and maybe the last hour you will be learning less. But if you continue, yes, learning, maybe you cannot learn anymore because you are so tired. You cannot learn 24 hours per day, right? So there should be a plateau. What else? But that will be like this. Okay, so what we are looking is feasible regions, okay? It makes no sense for us to look into regions of the problem that might not fit the reality. So we always have to find out which are the functions that might be representing the reality. What we do is we create a function like this one, and then we provide a set of restrictions. Another example of utility functions. Let's say that I have an experiment, and I'm telling you I have a coin, and with this coin, if it is head, I will give you 10 euros. And if it is loss, you give me 20. Who wants to play? It depends. There are people who want to play these things. So it will be based on what? on the utility that you get from a specific attribute, which will be maybe you are not risk, and this is the point, you are not risk prone. I will have to provide you with a big difference between what are you, I mean, I'm telling you like, if you give me €1 if you win, or if it's a toss and I give you 100, then maybe you will say, okay, now I play. Because the cost, the expected cost, in this case, so we know that, for example, people through time, they change the attitude about risk. Younger people, they are risk prone. Older people, they are risk adverse. Conservative. You have here different utility functions. So what it might happen is that what you want to do is to maximize utility, which is going to be AB, two groups. In this example, how much do you want from A? How much do you want from B? How much hamburger do you want? How much coolant do you want? And then this should be some kind of Pareto efficiency. So how do we find this? How do we solve this problem? Using search algorithms. And this is how these things are connected. Okay? This is also a part of artificial intelligence that it is connecting. Search, yes, searching with mathematical optimization problems. In this case, we have a solution will be 1. Why 1 is not interesting? Because you can do better trading some B for some A. 2, it is also not interesting because it is the other way around. So what you can do is go for 3, which is the tangent between those. Yeah. 4 is out of question because you cannot reach this state. This is what we call, for example, the Cobb-Douglas utility function, which is equal to A alpha. So, and there are many more. Questions? So how do you define utility functions? It is interesting for the search for knowledge. So how does it work? Until now, we have been focusing on this. You have a knowledge engineer, an expert, and then you are doing some kind of knowledge engineering, so you have a knowledge base, and you decide what to take data in a database, which data should be taken in a database, what things do we need to keep and things that we don't need to keep. And there's going to be a user that is going to be asking knowledge processing, let's say, user interface or program. Okay, give me a solution to a specific problem that I have. There are 2 different ways you can do that. I mean, you can look into the database, you can look into the environment, you can look into the expert, and they are going to be generating different kind of knowledge, right? If we are dividing machine learning again into different topics, we might have machine learning, deep learning, reinforcement learning, we have the robotics, and we have the reasoning. So until now, we have been looking into logical algorithms or algorithms based on logic. I want you now to start looking into machine learning a little bit more and understanding that the difference that we have between knowledge and intelligence. So it is not the same to have data than to have information, and it is not the same to have information than having knowledge about something. So people go to universities, and what I expect from you, it's not to have knowledge about something. What I want to work with you is on your intelligence to use the knowledge that I'm providing you. So for me, it is not interesting that if you are memorizing some formulas, it is also not interesting for me if you are memorizing some lemmas or if you are memorizing some algorithms. What I want you is to understand them and use them, use the knowledge. So I want you really to be solving problem persons. So let's think in AI systems again, reasoning and decision making. All the techniques that take into account knowledge representation. We have already seen this. We know how to represent knowledge in different forms. We know how to transform data to knowledge in different ways for different specific problems. And we can also make inference reasoning, yeah? So we can infer from a specific set of rules or whatever. We can write algorithms, we can understand those algorithms, we can work with them. Let's look into the learning. The machine learning thing is about trying to solve problems that you cannot really identify, they are not really specific enough. And the question is, which data, which methods? How do we choose the methods? How do we use the data that we want? And this is the part of artificial intelligence that it is very related to statistics, in which we cannot use any more symbolic reasoning as we have done until now, but we need a new set of tools. If you look into knowledge management in internet, you will have more than 100 published definitions of knowledge management. There are many. There are something that have a business perspective. All others is going to be based on cognitive science or knowledge science perspective or technological perspective. It doesn't matter. So it is multidisciplinary. There are many people working on knowledge management and how does it work. And you probably already use a lot of knowledge management tools. Can you name one? Do you have a GitHub? Okay. What else? Have you ever used a database? Sorry? Okay. What else? Yes, if it is used for not only for storing data, but it's actually can be useful somehow to someone. And this is the thing, you can have knowledge management strategies that are terrible. Like, for example, downloading PDFs with the name of the PDF that has been uploaded with 1, 2, 3, whatever. You can provide them with names. You can have it on Zotero. You can have it on a library. What else you can do? So the good thing about knowledge is that the use of it doesn't consume knowledge. It's always there. You can transfer it and you are not losing it. It's abundant. The question is how to use it. And what you have to be an expert in doing artificial intelligence is actually how to use the knowledge. And as you have seen, until now, what we have been doing is solving problems, right? So I have a problem, how to go from point A to point B. What can I do? Okay, I can use this algorithm, or I can use this other algorithm. I can use this heuristic algorithm, or I can use this heuristic algorithm with a specific distance, or with another one, right? So depending on how much time do you have, what is the outcome that the client wants, you're going to be using one tool or the other tool. The problem that we have is that for many organizations, they have a vast amount of information, and the information goes through the door when the people is leaving. So probably one of the things that you have to think about is how to start, what is your role as knowledge expert, yeah? Well, knowledge management objectives. So what do you do in order to, can you think on things that you do every day in order to, when you go to in this course, you don't need to take notes because it's too easy. But if you go to a different course that it is very, very challenging for you, how do you manage all the information that you get? What do you do? Do you have a kind of Nextcloud and Orna in your computer? Do you take photos? Do you take notes? How does it work? Takeaways? What else? Yeah. Yeah, and each one of you might have a different way to do it. And when you are working in a company, you should know how to do this. And actually, you might be even providing them with a hint on how to do this in the future. And most of the time, the problem that we have is that we go to a company, or a company comes to us and asks, can you do something with my data, please? Or, I mean, I have a lot of data. Do you have data? Yes, I have a lot of data. And you have to look into, okay, is the data, can I use it? Can I not use it? Can someone explain me something about the data? Do they have some documentation or not? How the data was generated and so on. So this is everything about knowledge management, okay? You have here some of the objectives that you might want to keep for yourself in the future. The thing that the step or the objective that I think is the most valuable for you in the future is going to be the last one. Build a toolkit of methods that can be used with individuals, that can be used with an organization, with groups, and that will diminish the risk in the future of losing something, also for yourself. This is why, well, there are key terms here. We have data, explicit knowledge, information, knowledge, raw data, tacit knowledge. Tacit knowledge is knowledge that it is difficult to explain. It is difficult to pass to someone else. It is difficult to identify, even to measure. Data, try to somehow connect some kind of knowledge to a specific set of strings, numbers, or symbols. But data per se is not knowledge. And if data is not well structured and it is not self-explainable, or it doesn't contain any information, then it is not knowledge. It is just data. And it can be noisy. It can produce nothing. So explicit knowledge, I mean, we can also have a look here. You have different types of knowledge based on 3 different characteristics. It can be general, it can be specific, it can be procedural, it can be declarative, it can be explicit or tacit. And you have different kind of knowledge. So let's say that you have how is this related to a real environment. Let's say that tomorrow a company is asking me, Javier, I know that you are an expert on any system optimization and you apply artificial intelligence methods. And I have a massive amount of data about the electricity consumption in the region. I want to find out how should I model the grid in the region so that in 2050 I will be ready and I will not have to invest huge amount of money because there are a lot of PV installed in the households and so on. So I need to plan how the grid, the electrical grid, will look like in 30 years. What do you think I do the first time? Huh? Okay, the data is a source of knowledge. Yes, I can look into data, I can look into the artifacts, let's say, practices, technologies, repositories of data, and so on. But probably that will not be my first step. My first step will be talk to people. Talk to the people who want me to work with them. I'm going to have workshops with them to understand what do they want to accomplish, why do they want to accomplish, what are the constraints, what are the sets of possible artifacts that I might be using, which are the problems related to maybe that they cannot give me the data, or they have to provide me data, but it's going to be anonymous, whatever. So what I need is kind of perhaps the tacit knowledge that we have, that they might have. I mean, I know that this is very abstract, but I'm telling you, this is completely real. I mean, you are going to be an expert on coding stuff that no one understands. You are going to be a magician for many people. Really, like you're looking like yes, like you are going to be like expert of the world. Like, please do whatever you want with me. Yeah. So of course you are going to be needing a lot of ethics in what you are doing in the future and guidelines. But you have to understand from where can you get data, because the data they are gonna do it very easy. They are gonna tell you, look, this is the database. Have fun. See you in 3 months. Give me the results. And you say, no, this is not working like this. I'm a computer scientist. Yes, but I'm not just coding stuff. I need information. I need metadata. I need to understand the framework. I need to understand how everything goes. Because you have knowledge management tools. Yes, but maybe they are bullshit. They don't work. The data is wrong. They don't provide enough information. It's not knowledge. Do you understand the logic? No. You can find different problems that you want to solve. The first one might be knowledge representation. How is the data stored? What do I see? It's a SQL database? Do we have vector data? Do we have images? Do we have raster data? Do we have maybe reports that we can use? What do you do if you have reports? Then you have to translate all these reports, digitalize them, and then find an NLP algorithm that identify everything that it is there, and then you have to populate matrix so that you can afterwards apply NLP. If they have recording, what are you going to do with the recording? You are going to see if you can understand who is talking or what is going on. Yes, to identify maybe things that has been said 1 year ago or 2 years ago or whatever. So there is a difference between how the knowledge was stored in the database, or how the knowledge was stored by the company, the client, and how to use it. And these things, sometimes they doesn't work. They don't go together. So maybe you have to do something there. And we are going to look into that. But before we look into that, I want you to understand what will be this thing that we are doing. And what we are doing is data mining. And why it is called mining? Exactly, because it's like a boom push wall, where you don't know what are you going to find in the database. Maybe you find a boom push or a pit or whatever, that it's destroying all the strategy because all the data that you wanted or whatever that you wanted to do, it is not possible. The data that you want is missing. Someone is deleted it. It was on the Nextcloud from someone, it's bye-bye. So in data mining, the first thing that you need to do is understanding what kind of data do I have? How do I solve the problem? What is the data collection procedure that they had? Should we implement something there for the future? Data description. What kind of data do I have? How can I look into it? And this is data science. Data mining is mining information to transform data into knowledge. Data quality and verification, exploration analysis of the data. Once we have finished this exploratory analysis, which is very similar to descriptive analysis, if you remember your courses about statistics, descriptive statistics, then we are going to be jumping into data preparation. And we are going to be preparing the data for the algorithms, for the real world, for the models, let's say. Selection of data, construction, transformation of data, integration, formatting. Do you understand these 4 different steps? No? Someone that doesn't. Selection of data, which data is actually there and I can use it. I was talking today with a friend that he told me, like, I have 3 gigabytes of data for Germany for this thing. I say, okay, great. Can you tell me for this specific variable, how much data do you have? And he told me, okay, at 0.1%. And I told him, okay, this is the important information. No one has it. Yes, but maybe if I look into another source of data, yeah, I've been doing this for 5 years. I still didn't find it. So good luck with it. Just talking with me, it's much easier than trying to find out how to do stuff. Domain knowledge. And this is why you have to have some kind of business understanding all the time through all the cycle. Construction of transformation of data. Let's say that I have data and is on a scale or on a kind of variable that I cannot use. I have to transform it. It goes from 0 to 1 million, and maybe I want to transform it from 0 to 1. Transformation of data. Maybe there are some variables that are discrete and they are only appearing in my data set a couple of times, and I want to make different groups based on some business understanding. The integration of data afterwards into a database, into a whatever framework you are using, and then the formatting of the data for the use. And then finally, you can do the model building. Many people say data science is a 99% of working with data and 1% of applying models. Well, it is true, but this 1% will define the other 99%. There is a RESP-DM, data mining process methodology. Have you ever heard of it? It allows you to identify all the steps that an expert on data science and artificial intelligence should take in order to solve a problem. And we are going to be following this through the next days. I want you only to understand how it works, because I'm not going to be repeating this in the future. So we are going to take a look into what are the goals, what do we want to do, what do we want to achieve with some examples, and then we are going to be starting with data. What kind of data can we find? We're going to be looking into tabular data mostly. Afterwards, we're going to be looking into data preparation. How to prepare the data, what kind of data structures do you want to use, what is the difference between a data frame, a list, an array, a vector, and so on. Then we're going to be looking into modeling. We're going to be looking into clustering algorithms. We're going to be looking into linear regression. We're going to be looking into quantile regression, and so on, so that you understand the different machine learning methods that we have. We are going to look into evaluation of those methods, how to compare them, how to see what is the method that is the better, or the ones that provide us with the best accuracy, and then how to deploy it. And how to deploy it, might be probably associated with how to write down a clean Jupyter notebook, how to write down R Markdown, and so on. And this is completely different to what we have done until now. Because until now, we were just looking into logic and looking into computer science algorithms and so on. And this is, as I told you before, we are getting outside of that. We are finished. We already finished with logic. We already finished with inductive reasoning. We are not going to do machine learning stuff during the rest of the course. Everything clear for everyone? Do you have questions? Okay. Then next week we start with the statistics. So please bring something to write down stuff and make formulas by yourself on a piece of paper or on your computer as you want. And in 2 weeks, we will be switching to online, because we will start coding machine learning. So we will be applying everything that we have seen until now.